Okay, here we are, the second video. I forgot to mention in the last video that generally speaking, I go back and edit these a little bit, but I actually don't have time. And so the quality may not be as much as it could be, but hopefully later in the quarter when I have more time, I will do a little bit better editing on these. So this is the quick overview of material in 133. So this is the material as I presented it. I'm sure students will recognize this. I know other teachers use my book, but I'm not sure to what extent they used it in, and so I don't know. I hope everything makes sense. Like I said, all this stuff is available on Canvas, but it's also available online and on a website called unconditionallearning.com. You can get everything from 133 off that website. So anyway, let's grind through this. So digital design, to me, it means it's the act of creating a digital circuit to solve a problem. There's many ways to solve problems. Digital design is using digital circuits. Digital design is, in modern digital design anyway, is hierarchical and modular, which means we toss together a bunch of boxes and call it a circuit, and that's the modular part. And the hierarchical part is we put all those boxes in a box and use that in other design. That's the hierarchical part. So the issue here is all these circuits are made up of just the same modules over and over again. We rarely have to write our own modules, and I call those foundation modules. They're just standard modules out there. I just gave it a pretentious sounding name. So two types of digital circuits out there, combinatorial and sequential. Sequential circuits are known to have memory. Combinatorial circuits don't. Technically speaking, combinatorial circuits, the outputs are a function of the inputs. For sequential circuit, the outputs are a function of the sequence of inputs. Yeah, there's the type of digital circuits again. So logic operations, there's only three really, is and or not. And we have those using gates. So, but also remember, a gate is essentially a piece of hardware that implements a logic function. But there's actually more gates than just and or not. Okay, remember, not's an inverter. So and or, NAND, NOR, XOR, and XNOR gates. So NAND, not and, NOR, not or. The XOR has a special function. Actually, it's exclusive OR, which means the OR function is actually inclusive OR, but we never call it that. And there's also an XNOR. So the issue of some of these gates are functionally complete. Essentially, the NAND and NOR gates are functionally complete, meaning that I can create any circuit possible using just NAND and NOR gates. Okay, AND and OR gates, XOR, XNOR are not functionally complete. So for example, for an AND gate, I can get an OR function out of it, but I cannot get a complement function or not or an inversion function out of it. Functionally equivalence is the notion of that. A lot of these digital circuits have many different functionally equivalent solutions, which means the input-output relationship is the same, except it's implemented in different ways. We can use different gates, different levels, all sorts of different approaches to implementing a circuit. And so we like to say this circuit is functionally equivalent to some other circuit, even though it's not really 100% equivalent. Yeah, so finite state machines are the key thing in the 133 course, and it's pretty much very important in this course also. So finite state machines, as we use them in 133, was a circuit that controlled other circuits, so essentially the controller circuit. There were two types of state machines, finite state machines. They were a Mealy type and a Moore type. The difference between the two types was the Moore type. It was the outputs are a function of the state only. Mealy type, the outputs are a function of the state and the external inputs. So three parts of a state machine. They have two decoders in them, an X state decoder and an output decoder. It also has a set of registers, which we refer to as the state registers. Decoders are combinatorial circuits. The state registers are, being registers, are sequential circuits. Lastly here, we did talk about setup and hold times. These circuits are physical devices. You have to meet certain parameters to ensure they work. So the setup time was the amount of time before, in sequential circuits, before that clock edge that the circuit's other inputs needed to be stable. The hold time is the amount of time after that clock edge that the circuit inputs need to be stable. This was a super important concept. We kind of brushed over it in 133 simply because it's something that's hard to test. The issue here is you can just speed up your clock cycle, and at some point your circuit's going to fail, and it's primarily going to fail because it missed a setup or hold time. So this is kind of the old version of a digital circuit where we have inputs and we have outputs, and inside this box here, this digital circuit, we have modules that are talking to each other. So inside this we have sequential modules, combinatorial modules that are talking to each other. So we want to move away from this and kind of modify a little bit to make it more understandable. And so what we're going to do is kind of classify the inputs and the outputs. So instead of just having inputs, we're dividing that in between data and control. And same, very similar with outputs. Instead of just having outputs, we have output data and we have status. Okay, so these are standard digital circuits. I like talking about these in terms of the new model for circuits. So this is a ripple carry adder. As you know and love it, it has data inputs, has a data output, and technically speaking, this carryout is going to be a status output, which matches this output here. There are no control inputs. Typically, combinatorial circuits don't really have control inputs. So I guess they do, but namely, this is a combinatorial circuit here. This is a MUX. It has data inputs and a single data output, and it has a control input. The control input decides which of these data inputs appears on the data output. This is just a generic decoder or anything I can implement as a table, like a lookup table. I'm going to call that a decoder. Standard decoders are a little bit different, so I classified these differently. So this generic decoder has data in, data out. This standard decoder has a select input and data out. These are more combinatorial circuits. As you can see, they'll have clocks here, and here's a simple register. Typically, we've got data coming in here, we've got data coming out, and then we have some control signals. This is a clock, and this is a load signal. Load controls, the load and the clock control when this piece of data is going to be loaded into this register. Hopefully that's review for you. Here's a typical counter. It has clock, and it has a data input, a data output. Counters are registers, so I do have the ability to load data into them. Here's the data input. Also, I have some control inputs. I can clear the thing. I can decide to count up or down, etc., etc. So generally speaking, most counters we use will have a status output, which is the ripple carry out, which hopefully that makes sense to you. You hopefully used that in your class. Very popular. I didn't put it in here. So in the end, we have a whole bunch of digital circuits, and they're under control of a state machine. So this is our standard digital circuit. It's being controlled by this control input, which is the output of a finite state machine. So this control connects up to this control. Something happens in the circuit, and the status is output from the circuit to the state machine. State machine decides what to do what to do next, what controls to send out next once it reads the status, etc., etc. So this is going to be the state machine is by all means a sequential circuit. Here's your clock input. So in the end, what we have here is a big circuit full of modules. All these modules are going to be controlled by something, and particularly what we're going to be controlling it with is a state machine. But in the end, this course is about building a computer, which is a microcontroller, roughly speaking. So we have two ways to control circuits, either with a state machine or with a microcontroller. The difference being that state machine is kind of hardware related. Microcontroller, you're going to control it by writing a program. You're not, I know this is completely unreadable, but in the book, I'm sorry, in the appendix of the old book and the new book, there's a list of all the foundation modules with pertinent information. I encourage you to go review that, take a look at it. And lastly here, so I included this in here simply because it's kind of what we're going to be doing in this class. We're essentially going to be building this circuit, and I mean, I guess it's given to you, but what you need to do is kind of understand exactly what's going on in this thing. This is a computer, or often we'll call it a microcontroller. Typically, I call it a microcontroller. But it has a bunch of stuff in it that certainly you're used to, and nothing in it is really new. I can go over it super fast here. This is a program counter. It's not actually a counter. It's actually a register, but no big deal. This is memory. This will be new to us. This will be talking about real soon. This is actually memory. We'll be talking about that soon. This is a combinatorial circuit. This is a combinatorial circuit. This is, you can see a bunch of muxes plopped around here. You know what muxes are. This is the ALU, arithmetic logic unit, which is another combinatorial circuit, no big deal. Here's branch condition generator, combinatorial circuit, which is effectively just a comparator. Here are your control units. So the control units actually broken up into two modules, which I'm not agreeing with that quite 100%, but we're going to go with that. So essentially, this is the state machine as you know and love it, and this is essentially a decoder that monitors inputs, sends out outputs. So this is the whole computer. Like I said, your mission is to build this thing and to understand it. I mean, anyone can build it from working off the spec here, but I want you to understand how these modules work with each other and what exactly the modules are doing, and we'll get into that more later. Okay.